In this section, we're going to talk about relationships between various kinds of spaces. So let's begin with n by n matrix A. Then we know that each row of A has n entries, or this can be identified as a vector in Rn. So we call that the set of all linear combinations of row vectors as the row space of the given space A. Of course, it is a subspace of R to the n. So let's see some examples using the matrix below. So suppose that A is given by this 4 by 5 matrix, and let's say this to be A transpose. Then the row space of A is by definition a set of all linear combinations of the row vectors, and the row vectors are simply the collection of rows, which is given over here. So the row space of A is a span of, I guess, 1, -1, 0, -1, and 5, and 2, -3, -1, -4, and 8, and 2, -2, 0, -2, and 2, and 1, 2, 3, 5, and 1. So basically, we are using the rows of A as a vector, and you can see that, well, these vectors are actually the columns of A transpose because we're switching rows and columns of A when you take the transpose. So the row space of A equals to the column space of A transpose. So in general, suppose that A is given by n by n matrix, then we can identify each row to be a vector in R to the n, and let's say R1 to Rn be that rows of A, then the row space of A is defined as the span of these vectors, and we've seen that the row space of A equals to the column space of A transpose. Now, the theorem states that two matrices A and B are row equivalent, then their row spaces are the same. So for example, like if B is in row echelon form, then the non-zero rows of B forms the basis for the row space of A. And even though it looks very similar to the column space stuff, but it is very different from those on the column spaces. So let's see some examples about row space and column space and the null space of the given matrix A. So suppose that A is given by this matrix, and let's say this one is the reduced row echelon form of the given matrix. Then we can certainly find the column space of A, right, by taking the pivot columns. So basically, we have pivot positions over here, here, and there. So the first and second and the last columns form the basis for the column space. So the basis for the column space of A is given by 1, 2, 2, 1, and -1, -3, -2, and 2, and 5, 8, 2, 1. So that we can tell that the dimension of the column space equals to 3, which is the number of the bases. And for the null space, we know that the dimension of the null space corresponds to the number of free variables in the homogeneous matrix equation, Ax equals to 0. And those free variables corresponds to the non-pivot columns in the reduced row echelon form. So dimension has to be equals to 2. And to find the basis for the null space, we have to solve this homogeneous equation, which is given by Ax equals to 0. So from the RREF, we can tell that, well, x1 equals to -x3 minus x4, x2 equals to -x3 minus 2x4, and x5 equals to 0. And the free variables are x3 and x4. So the solution set corresponds to -x3 minus x4 minus x3 minus 2x4, x3, x4, and 0, where if you separate the variables, that gives you x3 times -1, -1, 1, 0, 0, plus x4 Well, I guess -1, -2, 0, 1, 0. So this tells you that the basis for the null space equals to -1, -1, 1, 0, 0, and -1, -2, 0, 1, 0. And for the row space, so if you apply the theorem above, so the theorem says that the non-zero rows of B form a basis for the row space of A. So in this case, we have to choose the rows in the reduced row echelon form of A, which is given by here, here, and there. So the basis for the row space of A should be 1, 0, 1, 1, 0, and 0, 1, 1, 2, 0, 0, 0, 0, 0, and 1. So from here, you can tell that the dimension for the row space of A equals to 3. So one thing that I want to warn you here is these three vectors are not the first three rows of A, but they're the first three rows of the row echelon form of A. And in fact, we cannot use the first three rows of A as a basis for the row space of A because they could be linearly dependent. Or in other words, if you conduct the row reductions, then that certainly change the relationships between each rows. So we cannot guarantee that the original three vectors are linearly independent. So make sure you choose the vectors from the RREF of the given matrix. And for part D, if you add the dimension of column space and the null space of A, then we get 3 plus 2, that equals to 5. And also the dimension of row space of A plus dimension of null space of A gives you 5 as well. So suppose that A is given by m by n matrix, then the rank of A is defined as the dimension of the row space of A. So here, colon plus equals to means defined as in mathematics. So the rank of A is defined as the dimension of the row space of A, and that equals to the dimension of column space of A, which is simply the number of pivots. Then if you add the rank of A plus the dimension of null space of A, then we should get the number of columns of the given matrix that equals to n. So here, rank corresponds to the number of basic variables, and the dimension of null space corresponds to the number of free variables that add up to n, and the number of basic variables corresponds to the number of pivot columns, and the number of free variable corresponds to the number of non-pivot columns. And if you apply this to the transpose matrix of A, then we know that A transpose is n by m matrix. So these two adds up to the number of columns of A transpose, which equals to m in this case. And people call the dimension of the null space of A as the nullity of A. So that's why this theorem is called as the rank-nullity theorem. So let's look at this example. So suppose that A transpose is given by this matrix, and suppose also that the RREF of A transpose is given by this. Then again, the null space is defined as the solution set for the homogeneous equation Ax equals to 0. So in this case, I guess we have x1 equals to -9/2 x4, x2 equals to 3x4, x3 equals to -5/4 x4, and x4 is a free variable. Then this gives you x, the solution equals to x4 multiplied by -9/2, 3, -5/4, and 1. So we can tell that the basis for the null space of A transpose equals to the single set consisting of this vector. So the dimension for the null space of A transpose equals to 1. Then if you use this, we can find the rank of A transpose without doing any calculations. So by the rank-nullity theorem, we know that the rank of A transpose plus the dimension of the null space of A transpose equals the number of columns of A transpose. So in this case, it is 1, 2, 3, and 4. So from here, we get the rank of A transpose equals to 3. There is a geometric interpretation between the null space and the row space of the given matrix. In fact, the row space of A is orthogonal to the null space of A. And we will see this in chapter 6. And indeed, if you had the calculus 3, like if you take any vectors from the row space of A, say this one, then if you take the dot product between 0, 0, 1 and 5 fourths with the basis vector for the null space of A, which is given by negative 9 half, 3, and negative 5 fourths, and 1, that you will get negative 5 fourths plus 5 fourths, that equals to 0. And this is in fact true in general. There's a nice application of the rank-nullity theorem to find out whether there is a solution for the given system of linear equation. So let's pause the video and try out this problem before I give you the solution. So the problem tells us that there are 50 equations with 54 variables, and there are exactly 4 free variables. So let's consider a matrix A, which is given by the coefficient matrix for the given system of linear equations. Then we have 50 rows and 54 columns. Then we know that there are 4 free variables or 4 non-pivot columns. By the rank-nullity theorem, we can tell that, well, the rank of A plus the dimension of the null space of A should equal to 54, which is the number of the column of A. But we have the number of free variables equals to 4. So then we get rank of A equals to 50, where this was by definition the dimension of the row space of A. Then this tells us that there's no 0 rows in the RREF of A, or equivalently, each row has a pivot position, or equivalently, for any B in R50, we can find the solution X such that AX equals to B, or A is onto map. So for this reason, one can tell that any associated non-homogeneous system of equations has at least one solution. So we can extend the invertible matrix theorem. Suppose that A is the n by n matrix, then we had the characterization of the invertible matrices. But we can extend this characterization by using the various kind of spaces that we have covered so far. So starting from part C, so if A has n pivot positions, then we can tell that, well, there's no redundant vectors in the spanning set of the column space of A. Or equivalently, the columns of A form a basis of Rn. Or in other words, the column space equals to the whole space Rn. Once you have that, then the dimension of the column space equals to n, and this number equals to the rank of the given matrix. Or if you apply the rank-nullity theorem, then the dimension of the null space of A equals to 0, or in other words, the null space of A is simply the 0 vector space. So let us consider these two problems. So let us pause the video and try out these two problems before I give you the solution. So for the first problem, well, if the dimension of the null space of A equals to 2, then by the rank-nullity theorem, we have rank of A plus the dimension of the null space of A. Well, this should equals to the number of columns, that equals to 9 in this case. So we can tell that the rank equals to 9 minus 2, which is 7. And for the second problem, if the matrix is 5 by 8 matrix, then is it possible to have the dimension of the null space equals to 2? Let's analyze this from the rank-nullity theorem. So we have rank plus the nullity should equals to the number of column, in this case equals to 8. But note that we have the number of rows equals to 5 in this case here. So this means that the dimension of the row space or the rank of A should be less than or equals to 5. Or in other words, if you apply this to the rank-nullity theorem, we can tell that we have rank of A plus the dimension of the null space of A is less than or equals to 5 plus dimension of the null space of A. But we know that this quantity equals to 8. So this gives you the dimension of null space of A should be greater than or equals to 3. So in this case, we cannot have the nullity equals to 2.